All right. Let's get started. Hello, everyone. My name is Tomáš Drietomský. I'm from Slovakia, and I'm a data scientist at Mastercard for almost 3 years now. And today I'll be presenting generative AI merchant enrichment, or the game, how we call it. So we've built end-to-end Gen AI-powered merchant matching engine for the price of a ticket to the conference. And I would like to show you how we did that and what was driving our decisions when we were building up the methodology. So let's set up the context first. I believe that all of you can relate to a situation when you open your banking app and you see a transaction that you don't fully recognize. This particular transaction is from my trip to New York last year. And you can see that in the transaction overview, we have the merchant name, which is the SQ asterisk Sunshine Coffee Row, and the address is Larchmont. Well, it doesn't tell you much, does it? Mastercard has a transaction enrichment product that is based on Mastercard's real-time merchant directory that can help you with that and enrich the transaction. So what happens is that you send us over these kind of transactions, and we'll retrieve the complete information about it. So in this case, we identified that SQ asterisk is a Square, which is a payment facilitator. Sunshine Coffee Row is actually a merchant with its complete name is Sunshine Coffee Roasters. Then we retrieve the complete address as well, and contact information, latitude, longitude, merchant category, and many more. Now, let's discuss what's actually happening under the hood. So what you see over there is what we call a transaction descriptor. A transaction descriptor is a bank transaction message that can contain various entities such as payment facilitator, merchant name, street, city, zip, state, country, phone number, website, MCC code, and some other stuff. The game can handle variations of the unstructured transaction descriptors. So it doesn't really matter which entities do you provide, in which order. It simply doesn't matter anymore. So when it comes to the enrichment, there are two main parts. The first part is the entity recognition. So the LLM extracts key data elements from the transaction text and structures it in a JSON. So in this particular case, we are going to label SQ asterisk as an intermediary or a payment facilitator. We are going to label Sunshine Coffee Row as a merchant and Larchmont as a city. Now, the legacy solution was based on fuzzy matching logic, right? Comparing strings, calculating Levenshtein distance and the edit distance between the strings. It works, but there are serious drawbacks. Now, when it comes to LLMs, one of the main strengths of the LLMs is its generalization. So it recognizes the patterns beyond the literal text, understanding variations. When it comes to fuzzy matching, if you would have a truncated merchant like this, it'll be a huge problem. But LLMs don't really care about that because it understands the underlying context behind the text. Semantic understanding comes hand in hand with that. So the LLM understands that Larchmont is a US city, and it also understands the location hierarchy. So it understands that there are certain zip codes related to this city. It also understands that Larchmont is part of certain US state and US as a country, etc. In addition to that, we have cities which are present in multiple US states, such as Springfield, right? And the LLM also knows that, and that's all utilized while parsing these transactions. Now, the second module of the enrichment is the matching process. For that, we use another LLM that identifies the correct merchant based on the parsed information. So in this case, we put the intermediary aside because it's not really useful for the matching. So we just take the merchant name, we take the city, and we match it in Mastercard's merchant database. All right, let's dive even deeper and let's talk about the architecture. So the query contains the transaction descriptor, right? Sunshine Coffee Roasters. The first part is the entity recognition. So for that, we are using fine-tuned LLM. So for training, we have created train set, which consists of these transaction descriptors, and the expected output is the JSON with labeled entities. We are using Llama 3.1 with 8 billion parameters, and we are fine-tuning it via Mosaic API. All right, the second step, candidate retrieval. So the candidate retrieval part is based on the vector search. So we took Mastercard merchant database, merchant names, the address information, contact information, etc., and we have embedded it into the vector space using BGE small en, and then constructed a vector search index. So the input for this part is the parsed query from the entity recognition, and the output is top 20 candidates for a match, right? And we select these top 20 candidates based on cosine similarity. Now, we are in the third step, we perform entity linkage. So we take the parsed query from the step number 1, from the entity recognition, we take the top 20 candidates for a match, and we are using Llama 3.3 with 70 billion parameters to determine whether there is a match within those 20 candidates. If yes, we select the merchant record and retrieve the enriched transaction information. If there is no match, we simply say no match. This whole architecture is in our Databricks workspace and is completely offline. We are not using any third-party services, emphasizing the privacy. All right, let's talk about benchmarks. So what you see here is the benchmark for the named entity recognition part. You can see various Llama models, starting with Llama 3.1 with 8 billion parameters, 70 billion parameters, etc. We are measuring the success on precision here. So this is the foundation version. So no examples, just the best prompt that we could write. Now, when it comes to the prompt engineering, there are several strategies to be considered when you're building your prompt. One of them is including examples, relevant examples. Now, you can see there is only marginal difference in the precision when including more examples. And in the case of Llama 3.2 with 3 billion parameters, there is even worse performance because the model got confused with the examples. So based on our experience, there is a couple of concepts that we follow when we are building the prompts. So concise prompt versus detailed instructions. Based on our experiments, the longer prompts with detailed instructions yield better accuracy and more consistent results. When it comes to reasoning pathways, there are basically two main types that we considered. Chain of thought, in which you basically teach the model how it should think about your inputs and how you should lead the model to the expected outputs. While in the multi-stage approach, you break down your prompt into several smaller tasks. And then putting it all together. So how do we actually choose the best prompt? The obvious choice is you take all the prompts, you take all the models, you run your benchmarks, and you select the best one, right? That's what anyone would do. But something we consider while building the prompt is the instruction teachback. So we actually make the LLM to explain the instructions back to us so we can see that it fully grasps all the detailed instructions. And we've seen that, especially for the longer prompts, the LLM tends to prefer some of them and ignore the other instructions, which is not really good because then you're just making your prompt bloated for no reason. Now, fine-tuning. We were actually impressed to see how much does the fine-tuning affect the accuracy. And you can see that even in Llama 3.2 with 3 billion parameters, there was significant increase in the precision where we went from 52% to 96%. Some basic concepts that we consider when we are fine-tuning the models. So having perfect ground truth labels is an absolute must. And I cannot really emphasize this enough because incorrect and inaccurate labels propagate and amplify the errors. When it comes to the robustness, you have to make sure that your train set is diverse enough and you have to make sure that you're only including the relevant examples in your train set, because otherwise you're going to promote something that you didn't really intend to do when it comes to the predictions. And structured output design. So what we've seen, especially with the smaller llama models, is that let's assume we take a transaction that contains like a Walmart, and we've seen that the model will just keep repeating Walmart until it runs out of the context window. And that's why we are limiting the output, maximum output tokens by, I think, 1,000. But this is a problem with Llama. We've seen this in other use cases, and you simply have to manually intervene and just stop it, retry, and try to parse the transaction again. If it doesn't work out, then you just have to use the original input and proceed. All right, now let's talk about the embeddings and the vector search. So embeddings unlock incredible potential for the entity linkage problem, right? In natural language processing, I would say that the string similarity metrics are the standard. But when it comes to stuff like this, when you have Kentucky Fried Chicken and KFC, it's hard to find a metric that will tell you that these two strings are related to the same entity. Same goes with some locations, New York City and NYC. But it's not just about acronyms. You have Walmart and WM Supercenters, which stands for Walmart Supercenters, right? So there's no string similarity, but yet they refer to the same entity. When it comes to embedding model selection, the optimal choice depends on the data domain and task requirements. On the x-axis, we see the encoding time per query in milliseconds, and on the y-axis, we have the recall. Now, the marker size represents the model size in millions. Now, based on our experiments, and for our use case, BG small en and Ember v1 yield the same recall, but the thing is, BG is much smaller model, therefore it's cheaper to run it, and it's also much faster. So BG small was obvious choice for our use case. Vector search. So the key factors to consider when building a vector search is the data scale, accuracy, and latency. And you always have to kind of play with these three levers and find the right spot for your use case. Data quality. Duplicates and ambiguities hinder search performance a lot. So in our use case, we are retrieving the top 20 candidates, right, in the candidate retrieval part. Now, if you have duplicates there, you might, unfortunately, retrieve the duplicate records 20 times, and therefore you will never get to the right match. So data quality is super important. Input structure. So usually, especially when I was also attending other sessions, people are always having longer documents, and they are chunking them into smaller parts and then embedding them. We are dealing with quite short merchant records, so we don't have to chunk them. So we just have to figure out the right way how to structure them before we convert them into the vector space. So that's something that is significantly affecting the accuracy as well. And this is not really related to the building the vector search, but the K is the number of candidates that you are retrieving. And what we see in this figure is on x-axis, we have the relative inference time to the baseline where we selected 5 candidates. And on the y-axis, we have the relative match rate to the baseline of 5 candidates. Now, as I said, the sweet spot for us, for our use case, is K20. So yes, we increase the inference time by approximately, I think, 250% or 200%, and we gain around 50% bigger match rate. We could go with K80, why not? But it's just dependent on the use case, and if you can really afford that huge inference time. All right, now let's put everything together. So as I was saying, there are these strategic levers that you have to play around with to actually create a working solution that is satisfying your needs. Accuracy, speed, cost, and complexity. Now, when it comes to pulling these levers, as I was saying, the retrieval scope lifts the recall and the match rate, but it adds latency and throughput cost. Model size. Models with bigger models with more parameters, might increase the answer quality, yet they raise latency and the cost. Advanced reasoning logic. This is something we have tested a long time ago, where you basically take your input query, you take multiple LLMs, and you chain them. So you take the first query, you run it to the first LLM, you get the output, then you take both that, submit it to another LLM, and then do it again. Based on our experiments, if the first LLM is not figuring out your problem, the second one is unlikely to do it. So that's why we are just keeping it simple and using one LLM for the final output. Prompt length. So as I said earlier, longer prompts with detailed instructions yield more accurate answers, but it adds latency. And again, the instruction teachback. You have to make sure that the model is fully utilizing your prompt, so you're not adding the latency without gaining anything out of it. All right, and now some results. So this is the same benchmark as I showed earlier, but here we are actually categorizing the transactions in our benchmark set to 3 classes. Class A, easy. So how do these look like? So these are usually the complete merchant records. So when you have merchant name, street, zip, city, state, country, it's quite easy to match those because you have to match it on all these entities, right? So that's quite easy. On the other hand, it's also very easy to match certain merchants that are unique. So if I would have my own bakery, let's call it Tomáš's Awesome Bakery, in Prague, Czech Republic, where I live, it would be quite easy to match that because there's just one. It's not a merchant chain. It's not complicated. So these kind of transactions are what we consider easy to match. Now, when it comes to class B, moderate, these are the transactions that don't contain that many entities. So an example would be Walmart 1234, which stands for the store number, Houston, Texas, right? So we just get 3 entities. But when it comes to Walmart, there is a lot of them in Austin. So there's multiple stores, and the LM has to choose the right one. So it has to fully utilize the store number information and pick the right one. So the class B for us is when there is multiple relevant candidates, and the LM has to choose the right one. Class C. So the class C are the most difficult transactions where the legacy fuzzy matching system usually fails. These are transactions that are usually processed via payment facilitators, or they contain what we call dynamic descriptors. So some e-commerce merchants are actually submitting the order numbers and the transaction IDs into the merchant names. And each transaction is therefore unique. So fuzzy matching cannot handle that, right? Like you can have, for example, Amazon 1234, Amazon 1235, Amazon ABCD, whatever. And fuzzy matching cannot really solve that, but LLMs can, because it's simply detecting the patterns in the transactions and then parses it out. So the class C is hard. And now to wrap it all up, we can see that for class A, there is only marginal increase in the match rate, but for class B and class C, there is significant amount. And we are very happy with the performance so far. We keep working on it. We keep reiterating with our success team to make it even better. And yeah, the last topic I would like to discuss is how much does it cost to run game? And we'll break it down for each module. So when it comes to the entity recognition part, where the input is the transaction and the output is the structured JSON with labeled entities, it costs approximately $130 for one fine-tuning run, which takes around 27 minutes. So it's quite fast. We really love Mosaic ML. It's very convenient and very easy to use. After the model is fine-tuned, we use Databricks Mosaic serving, and that costs approximately $7.4 per hour because we are using the provision throughput. Now, the embeddings and the vector search. So it costs approximately $9.4 per hour to host our vector search, and approximately $2 to host the embedding model, which is BG small en. And then finally, the hosting of the judge, or the last model that is actually determining the match, costs approximately $48 per hour, which in total gives us around $70 per hour of running this solution. That will be it. Thank you very much for attending. Me and my team will be over there to answer any questions. So that's it. Thank you.